It's me, as person. Today, I wanna make a part two of this electron microscope thing, because I have an exam soon. So I thought this would be a good way to practice for the exam. So last time I talked about how the electron microscope works, how the beam gets to the material and the pattern. So today I wanted to talk about the most usual signals that one gets from the electron microscope. So there are the signals. They can be categorized into two types of main types of signals. You have elastic elastic scattering, and you have inelastic and elastic scattering and inelastic scattering. And so maybe I should talk a bit about what happens first. Otherwise it might be a bit confusing. So for both of these, they begin with the same. So you have the electron beam, which is very thin, but not infinitely thin. It has an area. One tries to make this area as small as possible. This beam, it's a material which should be known, consists of atoms. I mean, atoms or ions, or things with nuclei and electrons. Material typically consists of that. Some stuff scatters back. So that's what I mean with scattering. Something gets back. At least that's from scanning electrons. I mean, things scatter back, or things do scatter back with TEM. Or as well. So so you have TEM and SEM, where SEM, that's scanning electron microscope. There you are interested in what happens here, and not what can get through here. So this is what CMM is made really to detect. This is what TEM is made to detect. So a TEM can detect both sides, but it's more built to be and more useful here. I've looked this, have mostly about SEM, but yeah, I'll be talking about SEM stuff today, but this also exists. And can I be allowed to move this? No. Yes. No. Okay. I love you too. So select all. That's a useful function. So yeah. So what can come back here? So there are, like, as you can see here, two main types of scattering: elastic scattering and inelastic scattering. So the electrons here, they have some type of energy, usually called E0. So this is like the start energy. So with elastic scattering, what scatters back has more or less E0. So they are allowed to lose like up to 1 electron volt, but not really that much more. Inelastic scattering, that's so I just call it for elastic scattering. I just call it for ES, and inelastic scattering I call for IS, which would be pronounced ES in the region, and this will completely be confusing. But let's see if we can make it not confusing. So for elastic scattering, you will have the energy will be at let's see, we can see energy will be at E0. In elastic scattering, energy will be let's say, can write this in mathematic ways. So for inelastic scattering, you can describe the energy as this, as in between 0 and this beam energy, so E0. So from this you can see that inelastic scattering is, well, elastic here means that stuff happens without losing energy. So from that alone you can like see that this is true. Like with elastic scattering, you have the same energy in the stuff that scatters back. Stuff here for elastic scattering, that's mostly electrons. Or is it only electrons? Well, the example I will come up with, and the type that is most seen, most looked at, is electrons. So let's just assume for now it's just electrons. You can comment in the comment section below and inform me and everybody else if there is other types of elastic scattering. I will be very pleased. For inelastic scattering, so what is referred to is like the electrons will have this type of energy, but there are other types of signals that also comes with inelastic scattering, because the energy has to be lost to somewhere in inelastic scattering. So because like energy is preserved in the universe, so you can say for inelastic scattering the energy has to go somewhere, but where? So let's say maybe I can work on big documents, because I can I can go down here for elastic and rest for inelastic. So I can begin with elastic actually. So elastic. No, I was using some kind of elastic scattering. Writing it like this because I'm lazy. I can have it. It's a type of heading. Yeah, okay. I can. I can have this be like violet, because violet, like a reminder that elastic. Scattering is high energy. So okay, that's good. Okay, so just a reminder, E equals the beam energy. So this is when I pick up my notes. All kind of scattering you have, like that all kind of scattering that I can actually put here then. So now it has like the surface, and you have the beam come down here. Maybe go here, 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 here. It's like it's, and some beams resurface and goes out here. Something that I should maybe note here. Also some just disappear or into the material somewhere. So not everything comes out again. And yeah, something I should note is that maybe I should talk a bit about the electron. So electrons, they have wave properties. They have wave properties and particle properties. Imagine I spelled properties right here. Not properties or whatever I wrote there, but pretend it says properties. So an electron can kick out another electron as if it was a ball kicking out a ball from the electron, but it also have wave properties. Hence we can make these electron beams and have like optics. So like it works. Like we can use like optic rules on electrons, like the way light going through lenses. So yeah, like it's both a wave and a particle, and neither a wave and a particle, and it's super weird, and I don't know what's going on. I just become completely understand. I have no idea what's going on there. But so electrons, they are in shells. Some shells look like this. Some shells look more like this. But this isn't super helpful, especially not when talking about this. So, and this is more like probability charts, and I don't like probability, honestly. Yeah, an engineering student who doesn't like probability. Very good combo. So, because this can quickly get unwieldy, so use Bohr's slightly inaccurate models to explain things. And just so you know that this is slightly inaccurate, but good for illustrating stuff. 1, 2, 3, 4, 5, 6, 7, 8. So it kind of likes this. So yeah, ramble, and I'm never quite sure what direction I should go in. This is more useful for inelastic electron stuff when I come to explaining that. But so yeah, the electron is weird, and also the electron can go in weird patterns. One thing that is also useful to talk about later, but I've just decided to just talk about things early, is that materials have something called work function. This is just like energy the electron needs to kind of, like, how much energy does an electron need to just be able to buy material? I'm just running away, like just shooting out of the surface of the material. So that's work function. Why do I talk about work function suddenly? Because this electron, so to be able to scatter back, it needs some energy. So the electrons have gotten down into material, some dissipate into it, it goes deeper and deeper, it doesn't find its way out. And this here, it's found its way out and it shoots off into space or into a detector or into the laboratory somewhere. But it's not in the material any longer. So it's escaped the material. So work function, you can see that as a kind of escape velocity of escape energy. Yeah, and yeah, so to be able to be detected, so the detector is so here's the beam. So the detector grows like, remind me that I'm bad at drawing. So the detector kind of is divided into 4 parts and covers mostly up here. So it can have other configurations, of course. But this has some quite useful properties, which I can get into a bit later soon. So so yeah, you have detectors there. You can also have like just one detector or 2 detectors. That it's fine. Like it does the work as well. It does the work that as well. So so I've actually gone into something that is the main, or one of the main signals within electric scattering. Not the only one, but something that is called backscattered electrons. Or you can maybe you can call, yeah. So these has got the hilarious acronym BS. When talking about these you are like mostly talking about like probability that it is sent back, and And you can also talk about a coefficient or like a ratio of how much is sent back. So you have this eta, I think it's named. It looks like an N with a long leg, or a dragon head, or a strange N, eta. So and eta is then equals the number of backscattered electrons over the beam electrons. So the electrons that came with the beam. So that's like it's like a fraction of like, let's say a third of the electrons in the beam scatters back. Then this is a third. It can also be written as the current, or is it current or current density? Current of backscattered electrons over a current of beam electrons. Because if you think about it, this kind of makes sense. Like current, what is current? So current is like you have like this arbitrary area that let's say draw it a little bit better. So like a number of electrons go through, and you kind of look at over a certain time how many electrons, or how much charged particles is more right to say, how much charged particle has passed through an area. So that's more like what a current is. So then it makes sense to also say, assuming you have counted over the same time both the currents, it makes sense to like ask like also indeed like this is over a defined area, so it makes sense to like equating this. You can't like say current of backscattered electrons over number of beam electrons. It must be the same, of course, but this makes sense. So if 1/3 of the number of electrons is backscattered, it makes sense to say the beam of backscattered electrons is 1/3 of the beam current electrons. Or beam current, I meant. Yeah. One thing that is interesting is that this backscattering happens with interaction with atoms. So this is an atom. Yes, I model it as a ball. That's when it comes to modeling an atom as a ball. It's, you can argue how correct that is, but it's, yeah. Let's just say that it's okay to model an atom as a ball. One does it all the time in material science, so let's just assume it's okay. Any chemists out there might disagree. So and okay, it might actually be the core of the electron, then it's definitely the right, but let's say just atom for now. It might be the core of the atom, but I just say atom for now. So electron hits this, so now we assume electron is particle, but it is both particle and wave. And it's weird, just so it hits this, and it goes another way, so it's backscattered. Of course, it does backscatter quite many times to get back to the surface, and it goes down some distance, but if it goes too far down, it won't be able to find its way out. So what you can see here, if the atom is bigger, which typically happens if the, let's say, if the core is bigger here, if the core is bigger, there's a bigger chance that the electron will scatter from the atom. So there's like a long equation of that. Don't know if I want to spend time typing that off. But what is good to consider is that it is dependent on Z, the atomic number, so like if Z is big, there's this here eta is big, or bigger. A big Z means bigger eta. Small Z means smaller. I think I talked for a bit long. Smaller eta. Let's see. The other side of my notes, I have some notes here. It's something called studying. Let's see. Yeah, so something a bit curious is is that when the electrons go deeply, now this I just illustrate it as a big and a small electron. So like the sizes aren't different, but like this is high energy, this is small energy, this is like 50,000 volts, this is like 10,000 volts. So this will go, not that far into the material, but the chance of it scattering is not that great. So and for this will go quite far into the material, and the chance of scattering is quite high. So between these two, there is roughly 10% difference in eta. So like the coefficient of how much electrons scatter. Something that has a far greater importance when it comes to this, that is how the sample is tilted. So this is a bit harder to draw, honestly, but let's see if I can. Just imagine that was drawn well. So let's say here you have a sample with 0 degree tilt, and here you have like sample with, how much that is realistically like 50, but a bit more than okay, let's say this it should be 70% tilt, but I doubt that I found 70% really. But let's just say it's 70%. So you can like see more of the cone comes out here than it does here. So let's say it penetrates equally deep as it does here, but even though it penetrates as deeply into the material, it's still like a short way to get out there. So it's quite a higher probability of or higher coefficients of electrons scattering. I need okay. I should take a break because my voice. So the ether is greater here than it is here, because it's easier for the electron to get out there than it is to get out there. So therefore, high coefficients of electrons getting out there. There is a formula for this. I'll just write quickly. Eta of theta. There's a lot of Greek letters in science, so that's 1 plus cosinus of theta to p under 1, where p equals 9 over square root of z. So this really says n depends on n depends on theta and atomic number. So this is also, of course, oversimplified, but made something to work with. Let's see. Yeah. Next thing is inelastic scattering, and honestly, I need a break. So I wonder if I should split this up again and make the next part a part for you. Now I just take a break.